Today we're going to look at how we can change the form of a limit into something we can use L'Hopital's rule on. Now the indeterminate forms that we've looked at least some of them, the only forms that work for L'Hopital's rule is the 0 over 0 or infinity over infinity. And these last few problems on our homework, we're running into something like that or that, where we have to change the form depending on what the function looks like to make it into 0 over 0 or infinity over infinity. Now, some of the hardest ones to do that with are these forms here, where we have 1 to the infinity, or infinity to 0, 0 to infinity, or 0 to the 0. Now, when we think about those powers, we're not really looking at exactly 1 raised to a very large number. The value exactly 1 raised to any number, 1 to the billion, 1 to the 100 trillion, all of those would equal 1. But what we're saying here is the base is not going to be exactly equal to 1, but maybe approaching 1. Or the zeros is not exactly to the 0 power, but a power approaching 0. So that's why they turn out to be indeterminate forms. And we're going to look at an example here and see how to work with those types of indeterminate forms. Okay, let's take a look at this example, and this is actually number 52 on the homework sheet. But this one, we think about what indeterminate form we end up with. We're going to see x approaching infinity. So thinking about plug infinity in for x, we'll have infinity raised to the, 0 power. Infinity to the 0, that would be this form. But any of these forms the technique we'll use can work to solve that. What we need to think about before we worry about the limit, let's look at the function inside the limit. Let's call that y. And to be able to deal with an exponent with a variable in it, we're going to need to get that variable out of the exponent. What function allows us to pull that exponent out? Okay, the natural log. So what we're going to have to do is take the natural log of both sides, which is legitimate because we're looking at an equation. The left side is still going to equal the right side, taking the natural log of each of them. And at this point then we can use our log properties and pull the 1 over x out in front. And by rewriting that form then, we have natural log of quantity 1 plus x over x. Now remember, this is not our original function, but it's the natural log of that original function. And now we can take the limit as x approaches infinity for this form right here. What do we get? natural log of infinity is infinity. And of course, over the x as x approaches infinity. So,
Infinity over infinity.
right, we do turn it into this form, so now we can use L'Hopital's rule on it. Okay. So, we'll change our problem then to be the limit of this fraction as x approaches infinity. So we'll be dealing with this limit form, but remember, ultimately we're looking for the limit of y. This represents the limit of the natural log of y. Once we find that limit value, then we'll go back and see what the natural log of y does to it and how we can go back to the original problem. But with our infinity over infinity, L'Hopital's rule says this is going to equal what? Derivative of the numerator is 1 over the inside times the derivative of the inside, which is just 1. And then derivative of the denominator, probably do that in our sleep. And now, can we evaluate this limit? Okay, so 1 over, well, basically infinity. 1 over infinity goes to 0. So, what that is telling us when we look back at this, as x goes to infinity, the natural log of y goes to 0. We don't want the natural log of y, though. We want, what does y go to? Well, we can kind of look at this as if the natural log of y is going to equal 0 or is going to approach 0, what does y have to be? Okay. Natural log means base e, so y is going to equal what? Okay. Change the base here to an exponential. My little loop-de-loop thing, e to the 0 power is going to equal y, so y equals 1. So, as we kind of think in terms of the limit of y then is going to equal 1. So our original problem through this procedure will equal 1. Questions? Now this technique or this procedure we're going to use to develop what we know as the continuous compound interest formula. But before we look at that, let's go back and figure out how we find the compound interest formula. Now interest, simple interest, is interest is calculated by taking principal times the rate times the time. Okay. When we look at, say, compound interest, we're really calculating interest at a certain time frame and then adding that into the account, and that interest now becomes principal and earns interest itself. So compound interest, we'll kind of somewhat develop that formula. It could take hours to look at it in detail, but we'll kind of quickly, by example, show what's happening. Let's say we're looking at compound interest for a 3-year period, and we're going to compound it annually. Whatever principal it is, whatever rate it is, really isn't going to matter. Okay. And we'll just go ahead and use P to represent, maybe it's $1,000, maybe it's $100,000. Maybe you won the lottery and you're going to put $1 million in. Well, I don't know that any of us won the lottery, right? Although, was it just last week? It was pretty huge. But
be here if I won.
yeah, I don't think I'd be here if I won it either. So. But compounding annually, the way we do this, at the end of the first year, the interest we would earn would be the principal times the rate times 1 year. So the interest would be principal times rate. Now, how much would we have, what amount would we have in the account at the end of the first year? We started out with what? The amount we start with at the beginning of the year is P, the principal. And then at the end of the year, we add the interest in there as well. So at the end of our first year, not the 3 years, but the end of the first year, we have P plus PR in the account. We could say A is P plus PR. We'll say at the end of 1 year. Okay. Now as we calculate the interest for the second year, what do we do? The amount we have at the end of the first year will actually equal the principal for the second year. Okay? That's what we would have at the beginning of the second year. So the interest we earn on that second year will be, well, principal times the rate times time. We're talking about 1 year here, the second year of our 3-year investment. And let's see if we can't rewrite that a little bit to make it look a little bit nicer. Looks like we could factor out a P from that, right? Okay. Now again, that's just the interest. What's the amount that we earn, or the amount that we have at the end of that second year? Okay, it's going to be the principal for that second year, which is this, plus the interest for that second year, which, well, either form, but let's go ahead and show it as the little bit simplified form here. Now, we didn't do anything to rewrite this amount after the first year, but what could we do with that? Okay, we can factor out the p and make it look like that. So, and in developing formulas, this is what we have to look at. What is the process? Not what's necessarily the result, but what's the process in doing this? And we have the principal from our second year plus the interest from our second year. And how could we rewrite that one? Well, the form we have it in, we have two terms separated by that plus. Can we factor anything out of it? There's a p in both terms. Anything else that's in both? The binomial factor, 1 plus r. What's left in the first term?
1.
Okay, all that's left is 1 there, and plus, well, what's left in the second term?
1.
What may we want to do to this to make it even easier to look at?
Just make it squared.
Okay, we've got the p, and then we have two of the same factors, say 1 plus r squared. Now remember, that's the amount after the second year. What's the second year going to have an effect on here? What do you think? The value 2. Well, let's go through the third year and maybe it'll be a lot more obvious. So the third year, this is the amount at the end of the second year, which would then turn into the principal at the beginning of the third year. Okay, so we'll go through this same thing for our third year. The interest of the third year would be the principal, which was our p times 1 plus r quantity squared. Okay. That's right. That would be the principal at the beginning of the third year, and then times the rate times the time. Again, we're only talking about that 1 year, that third year. So time would be 1. And then the amount that we end up with at the end of the third year. Principal, the beginning of the third year, plus the interest for that third year. And how can we rewrite that?
Take out the p 1 plus r squared.
Okay, we can factor out that much. What's left in the first term?
1.
What's left in the second term?
R.
And once again, we can rewrite that even easier. And a quick little formula to calculate compounded interest over 3 years, okay, if it's compounded annually. Of course, if it's compounded more often than that, we'd have a lot more steps to it. But real quick, so compounded annually, what if we would continue this for 10 years? What do you think we would have at the end of 10 years?
plus r to the 10th.
And there's your formula, or there's the shortened version of compound interest compounded annually. Now, if we actually compounded this, well, sometimes they say quarterly, 4 times a year, we'd have, in 3 years, we'd have 12 calculations to do rather than just 3. Sometimes they compound it monthly. We'd have 12 times per year times the 3 years, we'd have 36 compoundings to do. So it gets a little bit more complicated when you throw that in. But again, if you do this step by step by step, you can see the pattern, even though it does get a little more complicated when n, number of times compounded, is not 1. What we find when we go to that extreme measure, the formula for compound interest is the amount equals the principal times 1 plus, now here's a slight change from what we developed. It's going to be R over N, where N is the number of times compounded per year, where we did it just once a year. That made the problem look a lot nicer. And then to the N times T. Now that, N times T, is really the total number of times we compound over a certain time period. Like we said earlier, if we compounded quarterly 4 times per year over 3 years, that would be compounding 12 times. Well, that's your exponent there, N times T. Okay. Now, this gives you a pretty good idea where the compound interest formula comes from. And we're going to look at how we get this nice short little equation when we talk about continuous. Does anybody know this formula? That looks familiar, doesn't it? PERT, principal, times e to the RT. Now, we're going to see how we can go from this equation down to this equation. The idea behind compound interest, N represents the number of times compounded per year. Quarterly, we said N would be 4. Monthly, N is 12. Daily, N would be 365. You could even go hourly, minutely, secondly. Well, N is going to get larger and larger and larger, and somebody came up with this brilliant idea of what if N is continuous? Or what if we continuously compound it? Which means N would be approaching what? So the problem becomes, how can we take this and find the limit as N approaches infinity? That is how we develop this formula right here. Well, we're going to have to use what we just did with the natural log. We take this as, say, y, and we're going to take the natural log of both sides. So y will equal the P times 1 plus R over N to the NT natural log of Y. Now notice we've got to take the natural log of everything. We're going to have a few more operations to work with, log properties to deal with. Very first one we have to look at is this product property. The log of a product is what? Okay, we add the log of each factor. So, well, that's not going to change much, but this one, this is what we want to look at. Pull the N times T and then times the natural log of 1 plus R over N. Okay. So as N approaches infinity, well, we're still not quite in a spot where we can calculate the limit using L'Hopital's rule, because we have infinity times, well, the natural log here, we'd have natural log of 1 plus 0. Natural log of 1 is 0. So we have the indeterminate form infinity times 0. But we need to convert that into either infinity over infinity or 0 over 0, which that's not going to be too much to trouble. One of the easiest things to do, in fact, we don't need the t, we really just need the n. We'll leave the t times the natural log. We can take n times something and change it to that something divided by what? 1 over n. So ultimately, we're going to be taking the natural log n approaches infinity of the natural log of p plus t times the natural log of that quantity divided by 1 over n. Okay. Questions? Now, as we work through this, we really don't need to bother with the natural log of p, because that is a constant in terms of n. Okay, in fact, we could have gotten rid of it from the beginning. The limit of a constant times something else is that constant times the limit. But we can deal with that later. The main part will be the limit of this second fraction. So let's focus on that. We have t times the natural log of 1 plus r over n all over 1 over n. Again, we said that would be 0 over 0. So L'Hopital's rule, now we're taking the derivative with respect to what? Okay, with respect to n. That's what we're taking our limit of. So t would be a constant then, and we'll have t times the derivative of this natural log. We'll do the shortened version up here. Derivative of the natural log is 1 over the inside times the derivative of the inside, Well, derivative of 1 is just 0. R over n, again with respect to n, r is a constant, but then basically it's 1 over n we're taking the derivative of, which would be negative -1 over n squared. Okay. And, well, right there we have derivative of 1 over n for the denominator part. So, what we have left then, -1 over n squared and -1 over n squared will cancel, and using L'Hopital's rule, we've gotten down to this limit. We'd have, we'll have the r times the t over 1 plus r over n. And as n approaches infinity, this part will go to 0, 1 plus 0 in the denominator. That limit equals RT. Okay? So, that's the limit. Where did we pull that limit out of? Well, we were looking at the natural log of y we had the natural log of y equaling natural log of p times that big ugly expression that we took the limit of, well, this thing right here. So that turns out to be just RT. Okay. Or I guess technically not necessarily equal, but it's approaching as we think in terms of limits. So we want to take y, well, to change from natural log of y to y is going to equal what? We'd have the base of e, so turn it into the exponential with a base of e to this exponent. And then with some exponent properties, adding exponents, we can rewrite and say e to one power times e to the other power. And then finally, e raised to a natural log. That right there simplifies to just the inside. So p e to the RT. And of course, I run out of room just when we're right at the ending. So continuous compound interest, the amount's going to be p times e to the RT. That's where that formula comes from. Now, you'll be able to do this procedure anyway. Like I said, those 5 problems you have left on the homework sheet, very similar procedure, looking at it as a natural log and then rewriting it, getting the exponent out, and then rewrite the limit as either 0 over 0 or infinity over infinity. So, any questions?